welcome you all to the second day of START 2025. Today, we are starting the first session on major milestones for Space Vision 2047, having 3 lectures. Today, there are 2 lectures, and the first one is on India's human space flight program, beginning of new era, by Shri Hanumantarai Balaragi. To moderate the first lecture of this session, we have with us Shri Abhishek Jha. I would like to introduce Shri Abhishek. Shri Abhishek Jha is the Deputy Director at the Directorate of Human Space Program at ISRO headquarters, Bangalore. He completed BTech in Mechanical Engineering from Vellore Institute of Technology with the gold medal and MSc in Computational Mechanics of Materials and Structures from University of Stuttgart, Germany with a merit scholarship. Shri Abhishek joined Liquid Propulsion Systems Center, Mahendragiri, presently known as ISRO Propulsion Complex, in 2009, and contributed in the development program of Indigenous Cryogenic Engine, CE-20. Since 2018, he has been serving at Directorate of Human Space Program in ISRO headquarters. Over to Abhishek.
Thank you, sir.
Maybe one of the mics can be switched.
Good afternoon to all. I am pleased to introduce Shri Hanumantarai Balaragi, Scientist G and Director for Directorate of Human Space Program at ISRO headquarters, Bangalore, to the participants and audience of the START program 2025. Shri Balaragi joined Vikram Sarabhai Center in 1999 and worked for 15 years for realization of launch vehicle hardware for PSLV, GSLV, LVM-3 and reusable launch vehicle. Since 2014, he is serving in ISRO headquarters and has contributed and supported approvals for various development and operational launch projects. He has completed Bachelor of Engineering in Industrial Production from BVV College of Engineering and Technology, Hubli, and received first rank to Karnataka University. Further, he completed his Masters in Mechanical Engineering from IIT Madras and received 3 medals for Best Academic Record and Project Work. Currently, he is pursuing his PhD at IIT Madras in the area of additive manufacturing. He is the recipient of 3 patents grants for research work in aerospace manufacturing and has published many technical papers and journals in national and international conferences. He has also co-authored a chapter for Handbook for Space Security published by Springer Nature. He is also a recipient of ISRO Young Scientist Merit Award, Same Yuva Anveshak Award, Benani Gold from Indian Institute of Metals, Best Idea Award by VSSC. I now request Director DHSP to kindly deliver his talk.
Sir, you are muted, I think.
Please unmute.
here. So I'll be talking on India's human spaceflight program. So beginning of in the new era with respect to ISRO's program. And I'll be covering on what are the activities we have done so far, then what are our activities in future, and what is the global status of our state of art activities. Then what are the opportunities for student community also I'll be covering at the end. So if you look at the birth of India's space program, so it commenced in 1960s with the first launch of sounding rocket Nike Apache to carry out upper scientific experiments in upper atmospheric zone. So it was conducted at Tumba, Trivandrum at magnetic equator where it passes. And subsequent to that, there are many applications where nucleated and demonstrated and understood that has got a great potential for the societal support. So the first experiment was conducted in 1975, utilizing foreign satellites, communication satellites, where that point of time India did not have any know-how about communication satellites, but that took us to learn many things and defining our own satellite systems. Then went on developing it. Today we have end-to-end applications, so catering to all kind of requirements of society. So similarly, from the development of a small satellite in 1975, we went on developing very complex communication, meteorological, cartography, all kind of satellites, including science missions. Now we have very advanced S-band or digital communication satellites. So in the area of rocket also, we started very small sounding rockets of 75 diameter, went on developing new bigger rockets. Then now we have a capacity of launching around 9 ton to LEO orbit. So we have all kind of all domain of expertise in the space program. So this is a summary of so this is a summary of India's space capability right now. So the fleet of communication satellites, navigation satellites, Earth observation satellites for various applications. And so we have conducted various from smaller satellite to very larger satellite of up to 6 ton size satellite communication satellites. And we have a fleet of launch vehicles started with SLV-3 and scaled up to ASLV. And now these two, SLV-3 and ASLV, are retired. Now, based on these two learning, so we developed a PSLV, GSLV with cryogenic engine and stage, and LVM-3, GSLV Mark III, capable of launching 4 ton plus communication satellites. So we also have all kind of applications. You can see here bottom the very high resolution picture that has been taken from Cartosat, and some of the application like monitoring disasters. So recent cyclones, 2 cyclones were simultaneously monitored by our satellite. So in all this, over all this some 7 decades of effort, so ISRO or India has conducted 99 launch vehicle missions and launching 127 satellites, and also supported 433 foreign satellites. And we also conducted several experiments so that including some of 3 of re-entry missions. So first one is in 2007, that is space recovery experiment. Then we did one more experiment, crew module atmospheric re-entry in 2014. Then we in 2018 pad abort test. So these all has led to a precursor technology for undertaking a human space program. So we also undertook, India also developed several satellites for space missions. So in fact, the first satellite that was developed by India in 1975, Aryabhatta was the first satellite that was for science mission. Then went on, undertaking several missions. So we have orbited satellites in Chandrayaan-1 in 2008. Then orbited satellites around Mars. Then we have a working astrosat in orbit now. So we undertook landing missions to Moon. Then we have a working satellite for L1 mission. Then we have recently done ExpoSat. So, catering to in adding to the previous what I've spoken. So not only we have a capability for say Earth observation, communication, we also have a capability for reaching to other planetary systems in our solar system. So in the nutshell, I can say that we have all precursor technology for undertaking human space missions. When you look at it, the global efforts, what has been made, initially, that adventure started somewhere in 1957. Then there were a lot of human space missions happened during 1960s and 70s. And that led, this all happened during Cold War time. And a lot of that is basically a race between the two bigger countries, and they also landed humans on Moon, and in several times by USA. Subsequently, the human space program was almost like limited to, like I can say, space stations. And if you look at the current scenario, so if you look at the right side of the graph, what I've shown here, there is a tremendous developments in space technology that is leading to have a low cost access to space. So improvement in technologies, new solutions, a lot of disruptions have happened that has helping us to have a low cost access to space. This is leading us that we can again start going again towards Moon or beyond for a sustained human presence. So these all technology maturity, low cost access have helped to think about what we can progress further for long duration missions as well as a sustained presence of human in space. So if you look at the current understanding of about the human health under microgravity or space environment, is our understanding is limited to the lower Earth orbit at present. And so now we need to, if I were to have a sustained human exploration in future, we need to have a gain understanding on deeper space, like to lunar areas. So now a lot of efforts are going on globally for a lunar gateway and reaching to establishing base on the Moon. And based on these understandings, definitely there is now a lot of effort towards defining missions for Mars. So that is also in the pipeline. So what has been learned now, incremental learning on the Moon and further going to Mars are the kind of plans by advanced countries. So there are many other use cases other than having a sustained human exploration. So it also lead to development of several scientific research. And when we do activities in the space where there is no atmosphere or oxygen and the environment is very hazardous, that leads to a development of several new technologies for human survival. And the space environment itself provides a lot of inspiration for education, for demonstrating many basic science principles. And if you look at the kind of some kind of threats what always Earth can have with respect to asteroid approaching with high velocity, and also if you look at that could be one of the reason where we need to find another safe place for this humanity to survive. Not only this, living and surviving in space also lead to development of several solutions, new kind of medicines in microgravity. Ultimately, all these lead to many economic opportunities on Earth. So this is what are the many other use cases for having or going towards sustained human exploration in future. Coming to human space program, that is our new era, what I am going to address now. This is India's vision now. So we have started a Gaganayan program somewhere in 2019 after taking precursor technological missions, what I have mentioned earlier. Then under this, we will be having, we'll be trying to develop and demonstrate the capabilities for crew transportation to low Earth orbit and bringing the crews back safely to Earth. Then subsequently, we need to have technologies for having sustained human presence in low Earth orbit, for which we have approvals, and we have undertaken the development of a Bharatiya Antarish station. First module of that is under development now, and this will be the logical step for crew habitation for medium and long duration space missions in LEO. And based on the learning and expertise on this, all this, we will be moving towards crewed lunar landing mission by 2040. So this government of India has recently unveiled this expanded vision for National Space Program, and we'll be having operational Bharatiya Antarish station by 2035, and having Indian human landing mission on to moon by 2040. So this is the overall vision right now we have, and we have been incrementally working on step-by-step technology development and demonstration. So coming to Gaganyaan, any human space mission when we undertake, there are so many elements that need to be developed and demonstrated. And some of the important elements we have listed here. The first element is the launch vehicle, and that should be safe for traveling crew. So we call human rating. So we call human rated launch vehicle. It will have extra design margins as compared to regular missions. So when you compare, the regular missions are generally designed for performance optimization, whereas in human crew safety aspects are taken into requirement here. So another one important feature in space missions or crewed space mission is the crew escape system. In case of any exigency or any failure scenario of launch vehicle, so the crew escape system has to take this crew module safely from that scenario, and safely carry to the safe place. Like we have a plan of safely landing on water. So this is another new development when we talk about a human space program. And in ISRO, we have developed the entire this crew escape system, and we have completed a static test of 5 solid motors in this system, and integrated system of crew escapes has been also tested in a test vehicle mission, wherein we simulated one of the above conditions. So in addition to launch vehicle and crew escape system, we need to have an orbital module, and which consists of crew module and service module. In the crew module, where crews will be staying, service module will have a propulsion system, and which will help the orbital module to like change the orbit, maintain the orbit, and provide all the services what is required for the crew stay in the crew module. So this current Gaganyaan program or orbital module has the capacity to carry up to 3 crews, and it can support a short duration up to 3 days. And the orbit of this mission will be around 400 kilometers. When we recover, will be recovered in sea, either in Arabian Sea or Bay of Bengal. So if you just compare the differences between the conventional space missions and human space missions. So I listed here when you call a human rated space missions, the design requirement itself will be based upon to accommodate needs of crew. So this becomes a new constraints in designing the launch vehicle, and they have to meet anthropometric and ergonomics requirement of a crew, and it has to ensure fundamental human physiological needs like human factors and life support systems have to be provided. And now crew is in the loop, so any scenarios that crew has to operate also need to be considered. Then crew performance, so that also need to be accounted while designing the vehicle. So this lead to the concept of human rating, and it requires improving the relative launch vehicle and increasing the safety through addition of as I explained, the crew escape system or abort system. So you can also see right side when you compare regular LVM3 vehicle and human rated launch vehicle. So you can see the numbers of with respect to margins, design margins, the approach design philosophy, where here we look for maximum payload capability, where in the human return launch vehicle we look for a crew safety at any instance. So there will be several new features like fault detection systems will be implemented, and propulsion systems are derated here. So because to have a better design margins in propulsion systems. And in addition to that, we also need to have a contingency plan in case of any exigency, like crew escape systems have been implemented here. So if you look at the various technology elements of engineering systems, so basically I already explained about human rated and launch vehicle and crew system. In orbital module, we require a propulsion, then thermal protection system. When it re-enters, it has to, the module will experience very high temperature. We need to have a thermal protection system to protect the crew module. Then we need to take into account of human factors. Human factor engineering has to be implemented. Then, for a recovery, we need to have several kind of parachutes that are of space grade in nature. So we also need to work on an end-to-end mission. So we need to account human physical limits, and and also we need to take care of avoiding black zones where no tracking facilities, all those things we need to take into account. And recovery operations, recovery assets, all have to be developed and implemented. So particularly when it comes to human, there are several human-centric systems have to be developed and implemented. So life source system, basically, this is being developed by ISRO now, and it requires a flight suit. Then we need to have a in-flight nutrition and health and survival kits. And in addition, we need to have a crew selection. Their training itself is another new domain activities for crewed missions. So we have selected for the Gaganyaan mission, 4 crews have been selected from test pilots, and they have undergone space flight training. Now the wing ceremony of all these 4 Gaganyaan have been completed recently. So if you come to Gaganyaan missions, so we are having there are main missions as well and test missions. So before undertaking main orbital missions, so we need to do a lot of tests on the ground, test in the flight in a test vehicle, and we need to qualify deceleration system by dropping, taking crew module and associated system in air, and drop and deploy and test all the various parachute systems and sequence of that. And so we have completed 1 test vehicle mission, and we have demonstrated the one of the abort scenario in the flight. So demonstration of crew escape system has been validated in that. So we have in Gaganyaan mission ongoing, we have there are 3 uncrewed missions and 1 crewed missions. So we are preparing for G1 now, in which we are planning to test end-to-end mission, and we will also execute recovery operations for crew module. And subsequently, in 2nd and 3rd uncrewed missions, we will be demonstrating and validating performance of various systems, including humanoid anthropometric test dummies, and repeat uncrewed mission will be there to meet the certification requirement. And we'll also undertake some of a few possible micro-gravity experiments. So with all this G1, G2, G3 experience, so we will be undertaking 1 crewed mission, that is human space mission protocol will validate in that. And crew rehabilitation also procedure also will be validated in this. And first time the crew will be in loop, that demonstration and pre-launch infrastructure will be validated in crewed mission. So with this, we will have a first phase of Gaganyaan mission, and this helps us to have a capability for transporting crew to low Earth orbit and bring back safely. So coming to when you want to have a sustained presence, there is a need for incremental technology development. So that also we have identified. Right now we have approval for all this, and the incremental technology like random docking, on-orbit refueling, and robotic elements, and having protection like micrometeoritic protection system, MMOD, and having radiation monitoring protection systems, space habitat design, and for carrying out microgravity experiment, racks have to be developed, and we need to have an entire mission operations management. Together, Gaganyaan, the technologies that are developed in Gaganyaan mission and technologies that are planned under precursor missions to BAS will lead to our own Bharatiya Antarish station and operation of it by 2035. So what we are planning to do is the critical technologies that are required for long duration human space programs are being developed, and these will be demonstrated in 4 missions. So we have approval for all these 4 missions, and we'll be doing first repeat crewed missions like H2 after the H1 mission under Gaganyaan. So this where we will be trying for all the maximum conditions, maximum crew, maximum duration, or capacity for life support. So all these things will be demonstrated in the H2 mission. So like I told, rundover docking is one of the important technologies, so which we'll be attempting in G4 mission. So where our crew module will be docking to available space station, where we'll be demonstrating interoperability of the module. And we'll be implementing some of the indigenous elements like viewport, all those things. So then we will also we will launch first BAS Antarish station. Then we will conduct our own orbital module docking to our Bharatiya Antarish station. This is a profile of missions for next 4 to 5 years. Subsequently, we'll be adding remaining modules. So then we'll be building this space station and make it operational by 2035. Subsequently, we will have crude and cargo supply missions regularly for carrying out various microgravity experiments. So coming to this Bharatiya Antarish station has got so many elements. It's overall it is built in 5 modules. It has an overall mass of 52 ton, and it will be modular in nature. It supports research, and it also provides many commercial utilization like space tourism and all can be supported. So coming to taking human research program, there are so many steps as I mentioned earlier. Our understanding as such now by like a global understanding is up to low Earth orbit. Then so now all the efforts are being made to understand the human research or human health effects of other like deep space going to moon. Then further based on that understanding, there is a plan to travel to Mars. So this is in a step process. This will be understood and mitigated, and incremental technology will be developed and missions will be undertaken. Look at it, effects of space environment. Basically, we call on Earth we experience 1G gravity, and on Moon it will be around 0.17. But when we are in between, like International Space Station and all, it will be like a microgravity of the order of 10 to the power minus 5 minus 6. So when we experience microgravity, it has a greater effect on our health. So we can see in the middle where the blood flow, the blood pressure will be varying across the body. So this has got an implication on the health. And on the right side has shown various effect on the various organs of human. And not only we have microgravity impact, there is also environment effect. There's a lot of radiation that is coming from various celestial bodies, including sun. That radiation has to be mitigated. So those radiations also will have an implication on our health. So we need to take all these factors into effect consideration while designing the space systems. So of course, these are the negatives or effects. Those have become opportunities for research. And on the right side, if you see, microgravity provides new opportunities. And the gravity, if you can see any scientific research or a fluidic system, if you want to work, all those get settled at one place. But in the microgravity, they get uniformly distributed. This gives the opportunity for building many materials in a 3-directional way. Of course, this can be simulated on ground like rotations and all, but they are all having again limited, not exactly replicating the microgravity environment in space. So we can create, as I mentioned, many ways microgravity can be created on the Earth. So these are the different ways we can do. Generally, we make use of these systems to validate some of the systems before we fly into space. So these drop towers, parabolic flights, sounding rockets, various means for various purposes, this facility will be available, made use and validated. Then we will put these microgravity experiments into space. So there are very important applications with respect to biology, space science, and system engineering. So it gives all kind of experience. So when you understand the engineering aspects, we'll be able to design and develop much performing systems for deep space missions. Understanding biology helps us to move forward from Leo to Moon and Mars. So various ways these all technology growth or a continuous improvement in technology will help us expanding human presence in space. So this is how various efforts have been done right now in Leo. So more than like 3,000 plus experiments have been conducted in ISS and various areas of research. New materials have been developed, new devices have been developed, and these are being even been implemented on the ground. So there are many opportunities for students. So if you look at many challenges also being offered by ISRO, many have been shown here. And right now it is going on Fly Me on Mars. Some of these robotic challenges have been it's currently going on. So you can go through our website regularly, and you will have all these opportunities. You can also participate with your own unique innovative solutions. So if you look at apart from this, various technical systems that have to be developed for humans' presence, but undertaking human missions to Moon requires carrying a larger mass to orbit. So that requires something like 50 to 60 tons of mass to be put in Leo for going to or putting crew on Moon. So for this, the current launch vehicle capability is limited. So we have got already started working on next generation launch vehicle having capability of up to 30 ton. Then we can have multiple missions and dock in space and move forward to Moon. So all these efforts also is going on parallelly, and with development of technologies for human presence in space, then these launch vehicles all put together, we'll have ability to travel to or land on Moon. So this is a long-term plan. So we also have a lot of missions in Chandrayaan follow-on. So Chandrayaan 4 and 5 also have been approved. Subsequently, there will be a lot of, again, Chandrayaan follow-on missions to have a lunar reach out. Then we will undertake landing missions later. So this is a vision. So as I mentioned, current Gaganyaan program with limited access to Leo, then subsequently having Bharatiya station with follow-on Chandrayaan missions, understanding on human aspects, various engineering aspects in Bharatiya station and Chandrayaan missions, we will be able to have a mission to crewed mission to Moon by 2040. So thank you so much.
Thank you, sir, for the wonderful talk. We'll have few questions and answers from the audience now.
Balragi sir, in the last session, there were some questions related to our Gaganyaan. So maybe I can just point out one question. One question is like this: what we have to do to become a Gaganyaan? You may unmute and.
Yeah. So, sir, we have a question from Mr. Sagar Kumar. What is a black zone when you define mission?
I mentioned in my explanation, the black zone is where visibility with respect to tracking. So being a crewed mission, so crew presence in the crew module, so there should be continuous tracking of crew module so that we should be able to recover the crew from the place. Otherwise, it's if there is a away, if it is not, if we are unable to see and track continuously, we may miss sometime. Finding crew module in water will be very difficult task. So we need to have a continuous tracking of crew. So that is why if it is not visible, that is called a black zone.
Sir, we have another question. It's on docking and how docking related technologies are useful in future of human spaceflight program, and how the upcoming ISRO missions will help in improving this technology, sir. If you can throw some light on that.
So as I mentioned earlier, docking is one of the important technology for having a Bharatiya station. As I also mentioned, Bharatiya station is built using 5 modules because it is like a living house or say the in-orbit scientific laboratory, we can also say. So that kind of size and volume cannot be lofted in a single or launch. So it has to be built by piece. So we are planning Bharatiya station of 52-ton weight is taken in 5 modules and built in the space. And when we have to join one module to other module, and that is where the docking comes into picture. So that docking first step of technology demonstration is planned in SpaceX. So that activities are happening now. And here also, similarly, there are 2 small satellites. They have again, we call it the target and chaser. So they will be docking each other. So the kind of sensor suit, propulsion, all that are being validated, and a lot of simulations are going on. So when we reach that, there is a safe docking zone or time zone. So that time the experiments will be conducted shortly.
Thank you, sir. There is also a question on the idea of Bharatiya Antarish Station and how it came into picture in aspect of space exploration, sir.
Yes, so in our vision, we have a long-term plan of by 2040 or up to 47 that our Indian should land on moon, and we also taken a clue from what is the global developments. A lot of efforts are going on by other advanced countries for human sustained presence on moon, then further traveling to Mars. So a lot of new developments also taking place in space that are enabling tech, and we are also have required technologies for taking crew to Leo. Then based on that understanding, we have a plan for going to moon. So in that sense, we need to have a first understanding of crew and the required technologies for transporting crew to low Earth orbit, and understanding health aspects, requirement aspects. Then once we have all these infrastructure, facilities, human research, understanding all, we should be able to take a crewed mission to moon. So that is where intermediate step of Bharatiya station has come into the picture. And this is one best approach to develop various technology and validate it before we go forward.
Sir, one of our audience,
as I mentioned, to transport crew to moon, so it requires a huge mass to be lifted from Earth. So that capability right now, it is not with existing launch vehicle like LVM-3 is a maximum now. Right now we have around 9 ton to Leo, and if for crewed mission to moon requires around 50-60 tons of mass to be lifted, for which we need a new vehicle high capacity vehicle. So that is what is NGLV has been conceived and it is being developed.
Thank you, sir. One of our audience members wants to know what kind of experiments do we envisage to conduct in space environments?
Yeah. So basically, the innovations that can be undertaken in microgravity has to be pursued. So two aspects are there. One is engineering aspect of the crew systems also need to be developed. So that aspect will be developed and tested in microgravity. Other aspect is human research aspect. Understanding the microgravity, that space environment and effects on the human health on various. I mean, I showed where the microgravity has the impact on our entire body, on various organs in various ways. All that research understanding has to be there so that we can have a mitigation for that. So appropriate health management and operations and crew exercises is living, all that kind of activities what is required to be in space for crew to be in space have to be undertaken. So initially all these things will be new, so we need to take it as a research activities. Once we become a known thing, it becomes operational activities. So both engineering and human research activities can be pursued.
Thank you, sir. There's another question. How are the goals and milestones of Indian human spaceflight program when we compare it with other nations' space missions, sir?
Yeah. The objective is not to just compare with other nations. We know that some of the nations have all these capabilities, but whether we know all those things is important for us to undertake our own missions, for us to undertake our own research in developing various technologies in microgravity and or on the human research. So these know-how and capability we need to develop on our own for us to explore space in future. So of course, other countries like USA, Russia have much more capabilities, and we are learning, we are picking up on those lines, and we should be able to take our own independent missions in those lines.
Thank you, sir, for the wonderful interaction and the enlightening us with the talk and answering all the questions of the audience. I hand it over back to Dr. Ravi to take the program further.
Thank you all, audience.
Thank you.
Thank you, Shri Abhishek, for nicely moderating the session. And also our sincere thanks to Shri Hanumantarai Balrugi, today's speaker, for providing an enlightening talk on India's human space flight program. Now we will move over to the next lecture. Today's the second lecture of this session is India's own space station, that is the Bharatiya Antarish Station, by Shri D.K. Singh, Director, Human Space Flight Center, ISRO, Bangalore. Before inviting the speaker, I would like to call Ms. Ramya to moderate this lecture of the session. And I would like to introduce the moderator. Mrs. Ramya V. is a scientist engineer with a career spanning 12 years in ISRO. She has worked as part of simulation team for Mars Orbiter mission and Cartosat 2D and launch support team for IIRS missions while at ISRO. Currently, she is involved in development of crew training simulators for Gaganyaan mission at HSFC. May I invite Ms. Ramya to introduce the speaker as well as to moderate this part of the session. Over to Ramya.
Am I audible?
Yeah.
Thank you, sir. Good evening, all. I'm happy to introduce speaker of the session, Shri D.K. Singh, distinguished scientist and currently Director of Human Spaceflight Center, ISRO. Prior to this, he was Associate Director of Space Application Center, ISRO. He holds an MTech in Electronics Engineering from IIT BHU Varanasi. Over his career spanning 35 years in ISRO, he has immensely contributed towards payload system design of communication satellites as well as the navigation satellites, that is the NAVIC series. His notable contributions include crew communication systems for Gaganyaan, space-based quantum communication system, space-based laser communication system, atomic frequency standard for navigation satellites, high-power microwave amplifiers, to name a few. He received ISRO Merit Award for the year 2013 and ASI Award for the year 2018 for his contributions towards spacecraft technologies. He was awarded prestigious membership of the International Academy of Astronautics in the year 2022. He has several national and international publications and one patent to his credit. With this brief introduction, I welcome Shri D.K. Singh as a speaker for this session. Over to you, sir.
Thank you, Ramya. I hope I'm audible and my slides are visible.
Visible, sir.
Okay, so this is a presentation which can be considered as an extension and further explanation to whatever Baluragi has presented prior to me. So I'd like to start my presentation with a very big picture which shows the artistic view of universe. And I just want to tell the audience that we are just a small dot which is not even visible. Our Earth is a small dot on such a big picture, and that humbles us and also challenges us to explore for the better understanding of mankind and improving the life of mankind. So all the space exploration programs, they are driven for the betterment of mankind, and there are other aspects which I will tell you. So I would like to start a little bit differently. So what do you know about the sun? So most of us will say that, okay, it is our nearest star and all of the planets move around it. And this is the picture generally emerges in our mind when we talk about sun and our solar system. Now, we worship it because this is the source of energy, and the existence of life on Earth solely depends on the sun. And we have a large mythology about sun, different stories. But the question comes whether this supply will be there forever. So the answer is no. The nuclear fuel which is there on Earth, which is the source of energy, once it gets exhausted, there is a very scary situation which is emerging. So what is that situation? Currently the sun's age is around, it's a middle-aged star, and it's about 5 billion a year old, and currently it is giving energy, very bright, but as the energy, the solar fuel exhausts, this is going to die. That is about 12.5 billion years of age. It's a very large scale to be worried for as of now. Okay, but the question will always be there that if that phenomena happens, whether we are ready to accept the extinction of human race. So if you look at the picture on the right top, currently Earth and Mars, they have the right temperature because they receive right amount of energy, neither too less nor too high, so that the life which is of our kind, the mankind and the plants which are here, they can definitely survive provided other water and oxygen, all those things are there. But once the sun comes to the end of life, the inner planets will be definitely, two planets will be swallowed by sun, and the Earth and Mars will represent currently whatever you are seeing, the Mercury and Venus. And this situation also will be there only for 500 million years. So ultimately, the habitable zone in our solar system will shift, but that also is not everlasting thing. So one of the reasons for going for human space exploration, there are many, but one of this which you can think of the ultimate reason is we need to find a new home beyond Earth. Another thing is, and we have to develop the technologies to reach there, and we need to develop the technologies to sustain there. So the current human spaceflight programs are a very small step towards this larger goal, which whole humanity should strive for. Now, when we talk about the challenges, because if you want to develop the technology, you should know the challenges. So we need to understand about the space. The space is a unforgiving place, everybody knows. Surviving environment is very difficult, and technologies needs to address this also is very difficult. So if you look at the challenges, there is no air, it's a deep vacuum. We effectively don't feel any gravity because it cancels out. Extreme temperatures, lot of charged particles shooting here and there. The radiation from sun and the galactic sources, they are coming. And a lot of space debris because of the man-made satellite, as well as the other cosmic particles, galactic like asteroids and meteoroids. All those things are the threats. So in nutshell, if you summarize the challenges, there is a acronym called RIDGE, R-I-D-G-E. So because we are talking about humans, so our main effort is what are the problems for humans. So the radiation is a problem. I have the slides to explain what are the problem. Isolation is a problem. You can't sit in a very small room for the years together or even for the days. Distance from Earth, because Earth will remain the control point for the next few hundred years of human spaceflight missions. So the distance from Earth, because you cannot attend the emergencies immediately. Absence of gravity and the hostility because of the temperature and other things. So these need to be addressed. So now we are talking about only the challenges which are posed because it has to be the manned space mission. Whether it is a short duration or long duration space flight, there are effects on all the parts of body. So in nutshell, everything degrades. None of our ability is going to increase once you go into the space because of the fluid shift. You get the motion sickness, your muscles degrade, your bones degrade. Because of the radiation, you run the risk of cancers because of radiation also. And because of the microgravity, your heart starts behaving in a very different way, which may sometimes lead to the failure of heart. Your immune system behaves differently. So these are the challenges of the human space flight. But despite of all this, why would you like to do it? That is the big question. So the answer is, if you look at the benefits of the human spaceflight program, whether we are able to beat the sun's death or not, but in the near term, there are many benefits, like there are medicines which can be developed in space which cannot be done on Earth. There is an opportunity to test certain medicines in space because the astronaut health is it is fast degeneration. So in Earth, there are diseases where you have slow degeneration. So you are getting an accelerated atmosphere, you can test certain medicines. Material science, because there is no gravity, the fluid mixing is very uniform. You can grow the crystals which are not possible to grow because of the presence of gravity and convection on Earth. Then you can develop you can improve your robotics technology, very efficient energy system. So one of the challenge in the long duration human space flight is how can you make a technology which will give you self-sufficient. Self-sufficient means you have only X amount of resource and you have to use the same resource. A true recycling, 100% recycling of resource has to be done if you want to really go for a very long duration space flight. So all these things and beyond this, international cooperation, then the inspiration to the students and the researchers. So many things are there. I will encourage you to go to the internet and read further. Now, everybody will ask, what is the proof? You are just telling that these are the potential benefit. But there are few examples I am trying to bring it here. So the space flights have given more than 30,000 technologies which are commercialized, which were developed only because of the space flights, including human space flights. So sunglasses, computer mice, magnetic resonance imaging, miniaturization of your medical systems, smoke detectors, quartz watches, barcodes. There are many things. Space shuttle fuel pump is a spin-off. Their spin-off is helping children to heal their hearts. Then one very interesting spin-off is moon shoe. So that to develop a low shock footwear, there were technologies, there were materials developed only for the moon landing. And that has caused the revolution in the, so you get the sports shoes only because of the moon mission. So these are some of the examples I tried to bring. Now coming to the space journey. So there are three categories currently all the agencies are working on. One is near our home planet, that is the space station. I will talk about it later. But why we are doing a space station? Because we want to go to moon, we want to go to Mars. So this is the intermediate stop where you mature your technology, you do all your experiments and then move towards the farther distances. Now, once you go to the moon, the new challenges will come because there is no air. So how do we do that? How do we stay there? More radiations and so many other things. Then the journey to moon is still viable and it has been done because it is around 4 to 5 days. But the journey to the Mars is much difficult because it is going to be a 6-month-long journey. So now that is the great challenge for going for the human missions. So these are the things which you have to address. Now, since the topic is the Bharatiya Space Station and what are the other space stations which have evolved. So if you look at the history of space stations, earlier stations were monolithic, means a single module launch and then the self-sufficient to survive. So those monolithic space stations, there are examples like Russians started first. So they put the Salyut station in orbit and it's about 20 ton, 90 meter cube class of station. And it could sustain for 6 months, about 11 crews spent 23 days. Soyuz 11 was the crew vehicle which docked with it. But that time, not much of the experiments were done inside. Most of the experiments were outside there. They installed solar telescope, X-ray telescope, and spectrometer and all. And it is known that they have done some military observation also, imaging of Earth. Now coming to the, of course, the Cold War era. So the US also launched their own station, that is Skylab. It was a much bigger station. And there also, it was in orbit for 6 years. And there they focused more on the research inside the station, including medicine and some sun and earth observation and habitability design. All those things were done inside. Now the stations started evolving. Then it's turn of Russia. So they came with a much evolved station. And this was the first modular space station where the different modules were launched at different time. They were assembled in space through a docking technology. And this was much bigger size, about 350 meter cube, 250 tons of the station. And again, the focus shifted to the biology and other advanced experiments on the station. Now, ultimate thing came. Now by that time, everybody realized that if we want to be a bigger station, we need to pool resources. We need to go for the international collaboration. So ISS was born. So ISS is a very big multi-modular station, and it kept on evolving over time. And about 1000 meter cube, 420 ton, and it can house more than 6 crew. And this station has transformed the future of human spaceflight, because this has given too much of data, too much of information, and too much of confidence to take these technologies further. Now, Chinese also, they started a bit late, but they launched 2 stations which were single module, experimented it for a short duration and deorbited it, and ultimately came with the Tiangong space station, which is a 3-module station. And there also a lot of microgravity experiments are being done. Beyond the national space agencies and government, there is a new trend in the current era, that the space stations are being built by the private players. So there are 2 examples of this. One is Big Love, which is a next generation commercial space station. And it is a kind of inflatable module. In fact, they tested their inflatable module by docking with the ISS in 2016, and they are working towards the full-fledged station. Now, Axiom is another company which is truly talking about a viable solution for a long duration LEO station, and they aspire to start building the station now till 2027. These are the baseline plan. We have not seen the first launch yet, but they are working towards that. But this is very similar to a multi-modular space station, which is targeted to support the experiments as well as tourism. So this is just the summary over the timeline, and where you can see that the stations evolved right from the 80s to till now, and there is a sustained plan for taking it further, and that is where we entered into the game, and we are trying to talk about our own space station, which is called Bharatiya Space Station, or BAS. So I will talk a little bit about this. Baluragi has already talked about this, that what are the objectives. I will not repeat the objectives, but I will tell what gave us the confidence to go for it. So it is not new that we are working on the technologies which will ultimately lead to the sustained Indian presence in the low Earth orbit, and ultimately leading to the Indian landing on Moon. So everything started from in 2007, when the space recovery capsule experiment was done, and to the surprise of all of you, we in fact carried the microgravity experiment on them in this 2007 module. Later on, we started developing the crew module, and we tested the atmospheric re-entry in the KR-1 mission in 2014. Then we tested certain pad abort technologies, certain escape technologies in 2018 and 2023. And we are very close to doing our first uncrewed flight, which will also validate the various technologies, which will allow you to ferry to space station. I always give this example that if you want to go on the Everest and stay there, you need a technology or means and preparation to climb it. You should have ability to come back to the normal altitude. Also, you have to build certain technologies which will sustain you at the peak of Everest. So the Everest peak can be considered as a space station, and Gaganyaan can be considered as your preparation or your ability to climb the peak and come down. Now, coming to the BAS 1, again, this is a transition from the LEO transportation to the human habitation in the LEO. Baluragi has already explained that it is a 5-module station with 3 inline modules and 2 across-line modules, with the provision of 2 Gaganyaan modules getting docked to each side of this. This is further explanation of our space station 1, 2, 3, 4, and 5, and this was anyway explained in the previous thing. So here just I want to a little bit elaboration on the different type of modules we have. So we have the base module which will be launched first, and that is a that will have the capability of servicing, habitability, and a life support system which is non-regenerative, means it will use the it will have a stored resources, the water, oxygen, nitrogen, and all these things, and manage the habitability based on that. We are also planning to put certain payload racks which will allow the Indian researchers to do the microgravity experiments, and then slowly this will evolve to the core module, lab modules, berthing modules, and after all these things are there, we have the full-fledged stations available for lot of research in the 0G. Now there are precursor mission planned beyond the Gaganyaan. We have another mission where the human in loop maneuvers will take place, because you have to dock to the station. Astronauts have to maneuver the vehicle which will dock to the station. So that will be the experimenting in S2. Then we have to develop the autonomous docking also. So that will be probably tried with any of the international station available. Then we will launch our first BAS 1 module. And then we will launch another Gaganyaan which will have the autonomous docking, and it will robotically transfer the cargo, maybe some experiment and some other things, and install inside the module. This is at that time we will have the full confidence to go to the next phase of building another 4 modules. So if you look at the inside, in nutshell, the blue zone is the main. So this also symbolizes the Earth, which is from the space, it looks blue. So in this zone, all the astronauts will be staying and conducting various experiments, and rest all other zones are for their consumables, for the propulsion. And the left side, it is a way to enter. You have the airlocks, and so this is the amalgamation of many technologies, launch vehicle technology, spacecraft technology, and some of the new technologies which is called life support systems technology and human factor technologies. This is just a sequence, not much relevant for today's presentation, so I will skip this. Now coming to the gamut of the technologies. So if you look at, so as I told that it is amalgamation of large number of technologies. At the core you can see the engineerings, which is structures, power, communication, propulsion. Then comes the new factors, the safety, emergency, life support, crew, comfort, and other things. So the safety will again involve the protection of crew as well as protection of space station from the orbital debris impacts and so many other things. So this calls for very careful consideration of optimum balance of all the technologies. So you need a life support system. So I will always give this example that Earth, you are trying to maintain a air conditioning room. You have indefinite resource available. You can draw any amount of power from the outside and manage everything. But in the space with the limited power, you don't have any oxygen or nitrogen available from atmosphere. You have to manage from inside. So these are the things which are very, very challenging in the space. Now, there are 6 different human-centric aspects which has to be addressed while you are designing. So habitability and work environment, because crew should be able to be there and work safely. Crew safety, human factors, its ability to do the task. Then crew health management, fitness, nutrition, well-being, and the human factors in the mission planning. Right now, we in the satellites, we don't plan the human factors. We have to plan that he is not available for 24 hours. You have to worry about the sleep cycle and so many other things. Then all these things, the crew should be trained. So the crew training on the ground. It is very difficult to mimic everything which is there on space, but still you have to train them with your limited ability to mimic everything which comes in the space. So when we are preparing for BAS, the human factor is a new thing where we have to do a digital simulation of the different aspect of human interaction with the station modules, how he will enter, how he will move his hand, whether his hands are getting more strained because it is in microgravity environment. The capability is reduced. So a good assessment of all these things. If the crew has to move certain thing within the station, how it is going to be done, everything will be a big planning, and you need to simulate everything, plan everything well in advance, and then only execute in orbit. For the fitness, so there is no gravity, so your muscles and bones are not loaded. Within a week, so you will start losing your strength. So strength has to be maintained, but you don't have a big ground for the exercise. You cannot put a big treadmill there. So even the exercising equipment and the design of exercise itself is in a technology itself. So what are the portions which needs to be stressed? So the ensuring crew health is also one of the great challenge. Then the life support system I was talking about, you have to manage, you have to scrub the CO2, you have to maintain the oxygen and nitrogen ratio, and this has to be pressurized very near to the, so you have to create a earth beyond earth. So there are 2 technologies, non-regenerative, which is going to store its own resources, which is going to be in the initial BAS modules, but ultimately we will launch a module which will make a regenerative ECLSS, which will almost recycle everything probably to the tune of 85%. So you will need resupply mission to replenish the loss of 15% resources periodically. Now I would like to just give you the flavor of few other things like personal hygiene management. So once you eat, you have to excrete. That is a human body. So in a closed environment, how do you manage that? So the space toilet also is a technology. Now, since this also will need air, now that air is a resource you don't want to lose. So can you imagine that your air from your toilet is getting flushed to your bedroom? It's unimaginable on Earth. But if you go to space, you have to filter it and use it. So the odor control also is a technology. So I'm trying to give you the flavor of different challenges. Now food and water. So food anyway is prepared on Earth as of now, till we get the technologies to grow the plant and maintain that full cycle of farming. So these are the, so how much food, what astronaut has to consume. Actually, the calorific requirement in space is more than what you need on Earth. More than 2,500 kilocalories per day is the requirement of astronaut to maintain its fitness. So very special design of food is done. It has to be stored at optimum temperature, and everybody would like to have the taste. So there is a psychology related to the food. You cannot just pop a pill of high energy and stay there. So it is a psychological requirement of astronaut to, when he is eating or she is eating, it should be earth-like taste. So that is one of the challenge. So the storage of food, warming of food, storage of water, dispensing of water, all these things are the technologies. Then there are technologies which has to be developed for the cargo transport, and this is just a typical resupply mission in the initial phases of BAS, where you have to carry the oxygen, nitrogen, then carbon dioxide scrubbing canisters, drinking water, then the solid waste tank, the crude violet storage tank has to be removed from there, and a new tank has to be installed. So these are the things. So there are things which you have to always carry up, and there are things which you have to carry down. So the resupply missions are designed to address that. There was a very interesting story that in the Soyuz, they used to dump the waste in orbit, and it used to get burned in the atmosphere. But that is no more the practice nowadays because of the different concerns. One more aspect of the Bharatiya Space Station challenge is the protecting the station from the micrometeoroid hits. Now, there the particles are traveling with the velocity of almost 7 to 8 kilometers per second. And if there is a head-on collision, it is almost, you can say that you can potentially hit a particle with a 12 to 15 kilometers per second of velocity. So if there is a puncture, everything is lost. So there are very specific design which is done to ensure that the BAS module or any space station module is safe from the debris hits. So like the man-made problems on Earth, we are spoiling our atmosphere. Same way we are spoiling the atmosphere by launching so many things in space and creating a lot of debris, which are the potential hazard for any space station because of very large area cross section. So the probability of collision increases. Now coming to the radiation protection. So now we are lucky that on Earth we have two protections available from the cosmic, galactic, and solar radiation. One is our atmosphere itself. Second is our magnetic field. So our magnetic field traps many of this radiation in the near Earth orbit. Now this trapping is a boon for us, but it is a problem for the space stations. So space station has to pass through these trapped particles. So that is a one continuous radiation particles are there. Apart from that, there are flares which will come from the sun and other sources. So the problem is twofold. So the space station, there are very special protections to be designed. Sometimes we try to leverage on the available cushions like water, and there are certain areas of the space station which has to be shielded more than other areas. And if there is an event which is predicted for a very high solar flare, the astronauts, they have to go into that shelter. So there are radiation shelters which are designed within the space station. Now, why we are doing the space station? Because we would like to conduct a lot of experiments in the different domain. I have few slides to cover that. Now, those experiments need a very specific racks to be positioned there, and where the experiments from the Earth will go, it will get plugged. The presence of human is utilized to conduct those experiments, and then some of the samples, they come back to Earth, and other cases where the data is there, the data is downloaded to the Earth. Now, another part is viewport. Ideally, we would like, for the safety purpose, we would like to have all metallic station. No hole should be there. But that is not going to give a good feeling and full application. So there is a viewport, which is a quartz, a very thick quartz, very specific design, a multi-layer quartz window through which there is a beautiful view of Earth. And that is one of the motivation for the astronauts and tourists to go in space and observe the Mother Earth from 400 kilometers, which is impossible from any other vantage point. But this poses a lot of challenges in the design. I don't think that you should go and read something about the viewport which is used on the space stations. Then preparation for climbing the Everest. The way you prepare for climbing the Everest, you need to have certain physical capability, certain mental capability, certain gears which will take you to the Everest, strong willpower, and lot of training, lot of acclimatization, lot of familiarity to those situations. Exactly similar things are followed for the training of the astronauts. But these things need a very, very huge investment because you don't get the natural sites. Like mountaineering training, you have the natural sites available, you can go and do that. But for the astronaut training, you have to rig up several infrastructures, and one of the like centrifuge to give them the feel of higher acceleration, which they will feel when they are in the launch phase. When they have to do some extravehicular activity, go out and do something. That training is done underwater with a mock-up of a station with a controlled density, a large pool of about 30 meter by 50 meter by about 12 meter depth or even more. So these things are capital intensive, but they are must for the training. Then there are a few other technologies. Docking any was discussed earlier. Earthing is another thing. Means you have to pick the module and change the position. That is also so a robotic arm. You must have seen in the space station the external robotic arm, internal robotic arm. Then the sensors which will precisely guide you for the docking. The thermal management of whole stations, then the electronics and communication, all these things are the challenging technologies. Now coming to once you have the BAS, what all you could do. So there are many things which can be done by taking advantage of 4 factors: long duration microgravity, exposure to space, unique view of our planet, and unique view of outer deep space. So these attributes enable scientists to do many innovative experiments, and also available of human which can do many things in a very short time. If you want to do a robotic operation of same, it may take very, very long time to do a very small task in space, but humans can do in a very small time. So that advantage is there in the orbiter. This slide anyway was shown by Baluragi, so I will not dwell on this. Now the domains for the BAS application, which we are using, that we can conduct the physical science, biological science, space agriculture, astrophysics, space manufacturing, pharmaceutical research, and since astronaut is available, that itself is an object for the research, so the human research. Now the SRE, I already talked about it. Only in the lower two, you see the isothermal heating furnace was one of the microgravity experiment, and other was biomimic material processing reactor. So these were the 2 microgravity experiments successfully conducted. Now I will come to the very recent mission, which was a POEM mission, where first time India has done in space farming. So the seeds were sealed in a earth-like closed compartment, and the water was kept separately, and it was injected when we were in the micro-G condition in the orbit. And you can see within few days, 4 or 5 days, we could see the seed sprouting. And so this is the first step where the cowpea seeds were used, and this is the seed which germinates very fast. That is why it was selected. So this is a very good platform for researchers to do the further microgravity experiment. But there are other opportunities where we are collaborating with international space agencies and creating the opportunities for Indian researchers. There are opportunities on the Gaganyaan mission. There are opportunities for I already said in the BAS. We are also trying to set up the facilities which will enable the researchers to validate their experiment on ground before going to the long duration in space. And we are going to handhold all the researchers to do these things. So these are the 4 options. Anyway, the sounding rocket, where a few minutes of high quality microgravity will be enabled. Poem already spoke. Gaganyaan is there, and then the space station. Now, this is a roadmap. If any of the researcher is interested in doing microgravity experiment, they can follow this process right from the ideation to taking it to the Bharatiya Space Station. And I encourage you to be the early starter and be the part of national mission of Bharatiya Space Station. Thank you very much for your patience here.
Thank you, sir, for an informative talk. Let us take a couple of questions. We'll wait. So there's a first question. Please add more light on the cargo transportation and how the crew will be able to take it.
Cargo transportation is identical to our Gaganyaan crewed module, but no crew. So we will store the cargo in the module in a very specific way. And in the initial missions, the robotic arm, we are placing 2 robotic arms inside the station. It will pull the cargo and take it into the BAS 1. But once the crew is there are very specific protocol which is designed for the cargo transfer from the visiting vehicle, we call it visiting vehicle, to the main module. So there is an airlock area where both the modules will be docked. There will be pressure equalization, then the hatch opening, then the visiting vehicle can be accessed by the crew, and it can be simply transferred to the, you can see the space station. Once the cargo goes there, one astronaut enters into the visiting vehicle and he simply throws it towards the inside, and another astronaut catches. So it is like a free floating the things which are transferred from the inside to other. But if we have very specific machines or payload rack, that will have a very specific protocol through which it has to be transferred.
There's another interesting question, sir. They're asking why robots cannot be trained instead of human beings so that we don't need the need for oxygen, health, and food.
The objective is when the sun goes out, robots are not on the threat. Okay, you cannot focus on the short-term goals. The other thing, the robots are task specific. They cannot be designed efficiently for multitasking. So a multitasking robot will be so inefficient, so bulky that it will beat the purpose. So if you go and read to design a particular task, the training of robot itself is a challenge. And humans, one thing I will tell that we are the one who can respond to unforeseen, unexpected scenarios, which robots cannot. So whatever the degree of AI, machine learning, whatever learning you do, if the scenario, so even with all kind of training, the efficiency of any algorithm is not better than 90% in my guess. But in the space, you cannot do the error even by 0.1%. So why you want to botch a whole mission because of a failure of robot? So any mission critical task will never be outsourced to a robot in the in the long duration missions.
There's a question on debris. They're asking that lots of countries are involved in launching a space station and there is a lot of debris. So how is ISRO managing that aspect?
See, existing debris, you cannot do anything. But for the future, there are international agreements where all of your launches, they have to deorbited once its life is over. Then, the debris can be there in the orbits where humans are not there. So the 400-kilometer kind of orbit is the most important orbit for us. So there are international agreements that after the end of the life of your space assets, you are supposed to deorbit it and allow it to the burn in the atmosphere. So that is how the debris are being managed. But currently the effect of debris, they are there. So there is a lot of which is called space situation awareness, SSA. So space situation awareness is where we map each and every object, we predict its orbital positions with time and compute the probability of hitting it to the station. If there is an increased probability, there will be a spatial maneuver done, which is called collision avoidance or debris impact avoidance maneuvers. So those things are done. So nothing comes undeclared. So everything is being monitored and we try to predict much in advance so that we are able to maneuver our path different from the debris path. So that is the current way of managing.
There's a question on extending our imagination like the movie Interstellar. They are asking whether we can have concept of O'Neill cylinder the way they are shown in the movie. Is it possible and is it feasible?
I think I am not qualified enough to answer, but I never say that nothing is impossible. So as our understanding grows better, many things which we consider is not possible will be possible in future. But as of now, we do not have any technology or any way to say that it is possible today. But it may be possible in future because our understanding is still evolving.
Yes, sir. This is it. Okay. Thank you, sir, for an informative talk. I hand over back to Praveen, sir.
Thank you, Ramya, for moderating this session. Also, our sincere thanks to Dr. Shri D.K. Singh for presenting an insightful and informative lecture on Bharatiya Antarish Station. With this, we are completing today's lectures and will be joining back on Monday at 3:30 p.m. to hear on India's contributions to exploratory lunar science. That is the third and last lecture of the present session. Immediately after that, we will be having another session, which is Steps Towards Space Vision 2047. And we'll hear on the lecture on microgravity and biology of living systems, challenges for human space exploration and new opportunities for research. So goodbye to all of you. And we'll meet.
Thank you.
Yeah.
Bye-bye.
We'll meet on Monday on the same time. Bye-bye.